All right, everybody. Welcome to another installment in Theory of Computation. Today we're going to be talking about regular expressions in the computational theory sort of way. You might see regular expressions as a powerful tool in searching or verification of forms or grabbing lexical pieces in a programming language. But we're going to use them kind of to build up our understanding of languages in the theory of computation sort of way. So what is a regular expression? So basically, a regular expression can consist of five different pieces combined together to form an infinite combination of different things. So if you start off with some input alphabet, a regular expression could be one symbol of those alphabets. So you could have, if your input alphabet is A's and B's, you could have just an A or just a B, and that is a regular expression. You can also concatenate them. Sometimes the concatenation is marked with this like little center circle here, but most often you won't see that in a regular expression. But you could have any string of A's and B's. So you could have B followed by three A's, or you could have BA, or whatever you want, any A's and B's. You can use parentheses in regular expressions, and they can help segment off portions of your regular expression if you need them to. It doesn't make a lot of sense to do that here. Not yet, but there are places where that will become useful. You can have an or, which we usually signify with a plus. You can kind of think of this like a union. So in this case, our example is our regular expression is either the string AA or the string BBAA. And so that kind of gives us a choice. And the last thing that we'll have, and usually if you have a regular expression machinery, you'll have more than this available to you. But the last thing that we're going to have available to us is a star, which says, hey, repeat this thing any number of times, including 0. So I put a little star behind AA. So that's AA star, which means I can either have as many pairs of A's as I want, or I can have no A's if I want, or I can have this string BBAA. So the entire language becomes something like BBAA, the empty string, 2 A's, 4 A's, 6 A's, or some even number of A's that comes from this situation over here. So let's look at one of our first regular expressions as an example here. We have AA or B star. And what this says is that I can take the choice AA or I can take the choice B as many times as I want. And each time that I make the choice, I can make a new one. So BB is a string in this language or in this regular expression. And AAB is also a string because I could take AA the first time that I do this, and then I could take B the second time. So if you start listing out some different strings that are in this particular regular expression, you end up with things like, hey, any number of B's, any number of A's that are even, but you can also mix those up. And so you might say, this is a string of A's and B's, any number of A's and B's, as long as the A's come in pairs, meaning you always have two A's together, which limits it a little bit. It also includes the empty string because I could choose not to take this at all. All right, so let's look at a couple of example regular expressions here. So here's a regular expression for all strings that begin with 0, 1. So I write 0, 1, and then I want to say anything can follow that. And so the way that I say any binary string is if I say 0 or 1 star. That means literally any zeros and ones in a row. And that becomes a very powerful tool as we're building our regular expressions as kind of like a wildcard to say, hey, do this any number of times. And the any number of times thing is any binary string. So if I come over here to ends with 0, 1, then I can just say, hey, it's anything as long as it's followed by 0, 1. And if I want a string, all strings that contain 0, 1, then it's literally anything as long as there's a 0, 1 somewhere in the middle, followed by anything. And remember, since this is 0 or 1 star, I can choose to take the empty string. So 0, 1 literally contains 0, 1, and that's okay. That works out. And one thing that I think is interesting, and if you just came here for the regular expressions, this might not matter a whole ton to you, but if you take a look at the finite autonoma that I would write, the NFAs that I would write for these three languages, they do look awfully familiar, and they have some correlation here that looks pretty amazing, stark, and obvious. That won't always be the case. Some languages will be much easier to write as an NFA. Some languages will be much easier to write as a regular expression. And using those and knowing that we can switch back and forth is extremely powerful. Okay, so it's your turn. Pause the video. Go ahead and read this. It's a regular expression for any binary string followed by an @ symbol, followed by one or more binary strings, as long as they're separated by a period. So it looks something like this in practice. One question you might have is, what if I have only one binary string after the @ symbol? And that would mean there are no periods. So I'll give you a second to think about this. I'll pause the video to give yourself a second to think about this, and then I'll show you kind of what we came up with as our answer. And that looks like this. And you might say, hey, any binary string kind of implies maybe no binary string, an empty string, and that might be true. We elected to add a 0 or 1 to force at least one 0 or 1 into our expressions here. So you can see our 0 or 1 star became a 0 or 1, 0 or 1 star. That was important to force something to exist so that the periods didn't show up without something on either side of them. And so this is what it looks like for us. I think the hard part is over here on the right, where we say, hey, append this period with any binary string any number of times that you want. So every time you decide that you need to add another dot something, then it has to have something behind it, and then it can have any binary string behind that. And then you can do that as many times as you want. So you can have dot whatevers. This is a piece of the puzzle for if you were writing a form validation for an email address. This is what a lot of your websites will use, something that looks like this, a regular expression that kind of does this form verification. So let's do another one that might be interesting. This one's pretty simple. This one's for phone numbers. I used square brackets for the phone number example down here because parentheses are part of our regular expression language for us. If you were using some regular expression engine, you might actually have a plus or something like that to handle this situation, but plus is in our regular expression language right now. But anyway, so pause it and see if you can come up with a regular expression for any phone number, right? That looks like this, where we're forcing these square brackets. Okay, hopefully you come back. This one is pretty straightforward. Oh, geez, I hope you've been able to see some of these things from time to time as I've been talking over them. But you've got these square brackets here, and then literally any number 0 to 9, and we're using this as a shortcut to kind of mean 0 or 1 or 2 or 3 or 4 or 5 or 6 or 7 or 8 or 9. Okay, let's move on. What are the languages of the following regular expressions? So here's a regular expression, and I'm asking what's the language for this. You may want to pause the video and think about this for a second. The language that we come up with is this is either, it's the strings that is either the string 0 or the string 1 followed by any binary string. But a better way to say that is any binary string that begins with a 1. So that's the language of this one. Let's look at the next one. I have to make sure we're clearing our hurdles here. Well, I can't show you this whole thing because the video is in the way. But go ahead and pause the video for a second and you can kind of see what this part is. Imagine that there was a parenthesis star here maybe. And then I'll just show you the whole thing. So maybe you can't do this one in the video here, but if you take a look at it here. So what you've got are letters or underscores followed by letters, underscores, or numbers. And that's usually the language of identifiers for, say, C++ or Java and many programming languages. So the question is, how would we write that as a regular expression? Well, it looks a lot like this. And if you were writing a compiler for a new programming language, you would write a bunch of regular expressions for a bunch of things. There is some exceptions here, which is, hey, but it can't be any of the keywords. But the way programming languages get away with that is, well, if that regular expression already matched one of the keywords, then it would never reach this point anyway, so that's fine. Okay, that's it for regular expressions. Hope you got something out of this. As always, make sure that you be kind to others. And of course, in order to do that, you have to be kind to yourself. I'll see you all next time.